Our next speaker is Gary Calnan, who's co-founder and CEO of Cislunar Industries. It's a space technology startup focused on developing, building, and operating metal foundries in space. And I think he's got an interesting concept because he's going to be talking about how do we mine stuff that we put up there already. So in this role, Gary's applying his diverse background in entrepreneurship, capital markets, and corporate finance to build a key component of the emerging cislunar industrial economy. He's got a BA in economics from the University of Colorado and a charter from the CFA Institute. He took action with his lifelong passion for space by completing the ISU Space Studies program in 2017. And now he strives to help lay out the foundation for a sustainable human presence beyond Earth.
Yeah, so as you heard, I'm Gary Calnan, co-founder and CEO of Cislunar Industries, and I'm happy to be here. Thanks for including me. This is an exciting, topic, obviously, and we see metal processing as fitting in clearly into the value chain for mining and using resources on the moon and in space. The way we're looking at things, we have the same, I think, as others on this panel. We have similarly big vision. We believe that right now we're seeing the beginning of a new industrial revolution in space, which will underpin the sustainable expansion of humanity beyond Earth. And maybe one day will lead to large rotating habitats such as the one in this image. Obviously, that's a little ways down the road, but we want to set our sights on big goals. The drivers of this current environment, we see this as being fueled by rapidly dropping launch costs and reusability, accelerating private investment, and really an intensifying geopolitical competition to put permanent bases on the moon, develop cislunar space into a viable economic zone. It seems like this has been tried before, but with the current environment the way it is, it seems as if there's real staying power for what's happening right now. So while much attention is usually focused in ISRU and space mining on mining for water, which for obvious reasons, this is going to be an important first step. For the in-space industrial economy to really flourish, metal resources sourced from space are going to be absolutely critical. Metal resources have been critical to industrialization on Earth, and they will be in space, and they need to be coming from space. Eventually, large quantities of these resources will certainly come from mining the moon and mining asteroids, but we should not overlook the material that we can derive from recycling space debris and future space hardware that has reached its end of life. This especially helps us develop these technologies that we need to lay the foundation for the future, in the near term. And regardless of the source of the material, the in-space metal processing is going to be essential to transforming these space-derived metal resources into useful end products. So with this in mind, my co-founders and I created Cislunar Industries a few years ago to fulfill this critical need. And we seek to create the necessary technologies to process and provide metal materials really wherever our customers need them, eventually throughout the solar system. And this would be in space or on the surface of celestial bodies. And obviously, our long-term vision for large-scale metal processing is going to require a robust space-based economy to be commercially viable, and that still ways out. At present, this really doesn't exist, but we can and we really must start to develop these underlying technologies now so that they're ready when this full economy emerges. And we can actually do this in a way that meets near-term needs and therefore acts as a bridge to get to this future. So to do this, we are creating right now in the lab where we're actually building this hardware, the Micro Space Foundry, which is designed to deliver small-scale, low-cost, distributed metal processing capabilities. This will enable enhanced debris removal, recycling of space debris, propellant production, and in-space manufacturing. And a similar device we envisioned would also be deployed on the lunar surface with some modifications to how it works, obviously. The system uses induction heating to make standardized metal rods. And these metal rods can be used as ingots to feed into downstream in-space manufacturing processes. And they can also, interestingly, be used as a propellant in metal-based pulse plasma thrusters, such as the Newman thruster and other systems that other companies are working on. Here I show sort of a rendering of the core of the system. It's really designed at this stage to be pretty small. It's about 1/2 meter in length. And here we have it shown with the Newman thruster on the end. But yeah, you can kind of get a sense of how big we're talking about here, this idea of having a distributed system. So how do we use this to get to that bridge? Well, we're going to start with, we think we can start most directly with improvements to debris removal concepts. Here we show the concept of including a Micro Space Foundry on board a debris removal spacecraft, which enables it to actually produce its own propellant. And the way this works is depicted here. On the left, you see a spacecraft that has, it could be a debris removal spacecraft. If it doesn't have our system at this point, it's out of fuel. It would normally have to deorbit unless it's nearby a propellant depot where it could refuel. But if you include the Micro Space Foundry and you utilize something like a Newman thruster for your propulsion, you can robotically harvest metal strips from this debris and feed it into the Micro Space Foundry, create propellant rods, and thereby refuel your spacecraft. And based on our early calculations, we've determined that if you're doing a LEO debris removal operation, you really need less than 10% of the mass of any object to be converted into propellant to be able to deorbit that object down to, say, 200 kilometers, and then return to any altitude in LEO and go on to the next one. To add a little bit more description of this mission profile, I sort of show the concept of operations here. We would launch the spacecraft up with the Micro Space Foundry on board. It would capture that first piece of debris, process that material, take it down into orbit. We can change inclinations as needed to adjust the RAN for the specific orbit that we're in. And then we can go back up to the next target and just do it all over again. And in this way, we think we can get, something like, really propulsion or propellant no longer becomes the limiting factor for this deorbiting mission. But of course, this is still just dropping things into the atmosphere. We see the next step of this, taking this one step further, instead of deorbiting objects, we can actually recycle them and thereby completely remove these objects in any orbit, not just LEO, by transforming them into resources. We do this by putting one or more, depending on the amount of throughput that you think you need for the application, space foundries on a partner platform. Something like an Anarax Outpost or an Axiom Station or Arcasys or whatever, some commercial platform that we can host it on, and then we send out spacecraft, debris removal spacecraft that have the ability to utilize metal propulsion to go out and retrieve space debris and bring it back to the station where we can process it and recycle it and turn it into materials for propellant and even for building large structures. And this removes it's really the only way to remove objects from higher orbits. Right now, there is no way. They present a collision hazard even after they've been placed into their graveyard orbit. And they're vulnerable to inspection and other things from adversaries. This kind of solves that problem while creating a cache of materials for future use once the economy is there. We also have the ability to, in this kind of scenario, to salvage components, to store components on the platform for later use and reuse just as they are without having to reprocess them. Let's see. So early on, just to give you an idea of the amount of potential material out there, when we were trying to figure out the feasibility of this concept, we decided to narrow it down to upper stages. Both because they are, sort of simpler and more they have higher composition of metals that we want to target, but also because, studies have shown that the upper stages, the large upper stages in particular, are considered to be some of the most dangerous debris objects out there. And if we were to remove, a relatively small number of them each year, it would help a lot to stabilize the debris population. I mean, obviously this may have, this is sort of accelerating as we launch more and more satellites in orbit, but we did look at it, and based on the space track data, we found that, for large upper stages, you had 1.2 million kilograms of materials in LEO across around 800 stages. And in GEO, we had 380,000 kilograms of material. And this was only what was listed. So there's obviously, as we understand, there's a fair amount more than that, but this is just what we were able to find on the public database. So when we go beyond this even a little bit further, and we start to look at other aspects of how we can use the Micro Space Foundry, we really see a lot of different applications for where the Space Foundry could be used. We expect to have multiples of this on the lunar surface, or a lunar version of this, or a version that's in the gravity well. We see it being used for asteroid mining missions, where you can process part of the asteroid and turn it into propellant to return the materials. Obviously, we already talked about the debris removal and propellant processing. And interestingly, we see even materials launched from Earth as being useful. If you have another version of the Space Foundry that's not just producing ingots, but rather is operating in a continuous mode, you can use the same system, the same concept to create very large structures that could then be assembled into trusses and the like, and that could be fed with feedstock that's launched from Earth as well. So really, we're sort of feedstock agnostic, and turning this into materials that can be used to develop this economy. And so thinking about, kind of understand the economics of this concept of each of these devices. Obviously, there's a variety of use cases, but we decided to just look at the very basic idea of propellant, or of material value. And thinking about it in a LEO context, based on our calculations, we've figured out that one Micro Space Foundry that's at only 6U in length can, with 1 kilowatt of peak power, can produce around 1.5 kilograms per hour. This would be 6 of our sort of standardized rods that we have conceived of. And then if you apply a 50% efficiency to that, you end up getting a production capability per year of around 6.5 tons. And then if we apply a $2,000 price point, was sort of based on discounted LEO launch costs, which obviously that moves up and down depending on how launch costs go. We're looking at over $13 million just for each unit in material value alone. We can add value to those materials by creating them in ways that can only be done in space, or selling them for propulsion in scenarios where that's necessary. There's additional ways that this system creates value. So we think that it does show a way of creating a feasible business case here as well. And also, because we're trying to target a smaller scale, smaller form factor, the roadmap to achieve this is much more achievable and lower cost to get off the ground. And to that point, our roadmap, as we look forward, how we get to the end game here. Right now, we're working on our lab bench prototype. We have a NASA SBIR that we're working on for studying recycling metals in space using this system. We are planning to have a full-scale lab bench demonstration of metal going in one side, making rods, and then sending that down to our friends at Newman Space to show that we can make propulsion from it. So we could show metal in, propulsion out. Then we hope to move to a parabolic flight to demonstrate the capabilities of shifting the structure into something that could function in extended microgravity. We want to do an ISS demo of sort of our minimum viable product in 2023. And we're also thinking about a lunar demo of a very similar system as the ISS version in the 2024 timeframe, with a first commercial version of this device ready in the 2025 or so. And that lines up well with the companies we've talked to who might be interested in using this kind of technology, who are doing debris removal. This fits with their time frame. So we think that there's a really solid chance that this all kind of comes together well. And as the other speakers have said, like we also believe that we're not trying to do everything ourselves. That it's absolutely essential for all of us to cooperate and collaborate on this to make it a real robust industrial economy. And our focus is on metal processing and finding ways to use metal processing systems to turn these resources into this key critical piece of the puzzle. So with that, I will pass it on to the next speaker. Thank you.
Thanks, Gary. Very interesting. I'll be interested to hear what Chris Johnson has to say about the legal issues associated with cutting up other people's or other countries' satellites.
Yeah, only with their permission.
Well, even with their permission, it's kind of problematic under the OST.